Okay. So, I think we can start. Now, yesterday we started discussing about Bayesian linear regression, and we did compute up to the posterior distribution of the weights, but we did not complete it. To be specific, we did not compute the predictive distribution. But even in the posterior distribution, there was a small mistake I made, which I was hoping you should have pointed out, but you did not. But and I will first clarify that part so that there is no confusion, and then we will proceed. Okay. So, if you remember, yesterday we computed the posterior distribution, right? And in the posterior distribution, what was Sn inverse? The posterior covariance inverse of that. What did I write? If you recall, I wrote it as alpha plus summation I equal to 1 to n beta phi xi phi xi transpose, right. This is what I wrote. Do you see any potential issue with this expression? So, remind me, what is phi of xi? What is phi of xi? These are the basis function for the ith data point, but this is a vector. This is a column vector. So, how will phi xi look? Phi xi looks something like a column vector of dimension k plus 1, phi naught xi, phi 1 xi, and then it will go up to phi k xi, right. So, this is my basis vector, basis function vector evaluated at the ith training input. So, this is the basis function vector evaluated at the ith training input xi, right. What is the dimension? K plus 1 cross 1, make sense. So, this dimension is k plus 1 cross 1. So, then go up and look at the right hand side, I mean the second term in the right hand side. What is phi xi transpose? What is the dimension? K cross k, and it should be, right. Yeah, k plus 1 cross k plus 1, right. So, this dimension, if you compute it, it will become k plus 1 cross k plus 1. So, this is a matrix. What is alpha? Scalar. How can you add a scalar to a matrix? It is not element wise. If you add element wise, then even the off diagonal terms will come. Remember, alpha was supposed to be alpha I, because it was alpha W transpose I W. So, here the I should be there, where it will be an identity matrix of dimension k cross k. So, this I did not write in yesterday, because in my mind I was looking at alpha as a diagonal matrix with alpha in the diagonal, but I never specified that, and initially I specified alpha to be a scalar. So, that would have created confusion. So, this is one thing you should have noticed, that I was making a small mistake. Where? Yeah, so that I can take, that is not a problem. So that is the thing. So, what is inside is Sn inverse. So, that is the term I am writing. So, that is this one only. So, whatever is inside after W transpose, it is supposed to be Sn inverse. So, that is this term. Okay. So, you have to be careful with the the vector dimension, otherwise you will be in trouble. I mean, if you try to write a code without I, it will throw error, dimension mismatch, right. Now, it is clear, right. Okay. So, now we will come back to this slide, but so I have made a review slide which basically reviews everything that we covered yesterday in Bayesian linear regression. So, the first one is showing you the likelihood, right. The second one is the prior written in complete form. I just wrote it in proportional form, but it is the complete form. And then you have the posterior third row first column, right. And where Sn inverse, there is alpha I. So, that is the I, that's why it should be there, okay. It should not be alpha. And then the recursive formula we did talk about, that you can do it recursively, that is the fourth row, okay. And we did saw yesterday that how you can do things recursively, right. We did see that, okay. So, now the expression that we got was this one Sn inverse. There was another expression we got, which was what did I call it, m, right, m or mu, I think, okay. The other one we got, I think yesterday I was using mu, right. So, mu n, and mu n was equal to Sn, and then inside summation I equal to 1 to n beta Ti phi of xi, right. This was the mu n that we derived yesterday, okay. Now, when you will actually write a code in today's time, be it Python, be it MATLAB, whatever you use, you will actually like to use or do things in a matrix form. You do not want a for loop, because with a summation you will have a for loop, and that is not probably something that you will want or you will like to have. So, you will want to do things in matrix notation. So, if you have to do things in matrix notation, then the question is that how can you write this in matrix form, right. So, in matrix form, to write this I first have to define certain matrices, okay. So, first, so to write in matrix form, we have to define certain matrices. The first matrix we will define is capital phi, okay. This will be a matrix where of dimension n cross k plus 1, where n is the number of training samples. So, the training sample will be row wise, and the basis function will now be column wise. So, then can you tell me what will be the first row be like? What will be the first row? Phi 0 x 1, phi 0 x 1, second one phi 1 x 1, and it will go up to phi k x 1, okay. So, this is basically the transpose of the matrix or of the vector I wrote earlier, right. So, you will basically transpose it and then stack it row wise, okay. The second one will be phi 0 x 2, phi 1 x 2, and then you will go up to phi k x 2, okay. The last one will be phi 0 x n, because you have n training sample, n data points is what we assumed, phi 1 x n, phi k x n. So, this is your matrix, and this matrix has a name. Anyone know what is the name? Design matrix. This matrix is known as the design matrix, okay, where each row represents one training sample, each column represents one basis function. So, if you fix a column, the column will represent the basis function. If you fix the row will represent the training sample, okay. So, this is one matrix I have defined. I have to define one more matrix or vector actually. So, I also have the target T, right. So, T will now be a vector. T will look like T1 T2 up to T n, because I have n outputs, n targets corresponding to each x I have one measurement of T. So, corresponding to n x I have n measurements of T. So, this will look like this. I have also the weight vector, which actually will not change. So, the weight vector will be W and it will be W 0, W 1 up to W, what is the dimension? Up to W k, okay, up to W k. The total element is k plus 1, you are right, but since I am starting from 0. Okay. So, these are the three things I will need. Okay. So, just for completeness, phi is now a matrix which is of dimension n cross k plus 1. T is a vector of dimension n, and W is also a vector of dimension k plus 1. Okay. So, now things are in a matrix form or a vector form. So, matrix vector notation, and with this my Sn inverse will now be alpha I will remain as it is, okay, where I is a k cross k, plus beta was outside the summation, it is a scalar, it will remain as it is, and then you will have phi transpose phi, okay, because what was previously a column vector is a row inside this. So, the transpose is exchanged and only then you will get a k cross k. So, from dimensionality also you can write that. Similarly, mu n will be equal to beta will remain, no, Sn is first actually. So, mu n will be equal to beta, which is a scalar, Sn, which is a k cross k, then phi is there, phi transpose T, okay. Phi dimension is n cross k plus 1, when you take a transpose k plus 1 cross n, T is n cross 1, so you will get k plus 1 cross 1, Sn is k plus 1 cross k plus 1, you will still get k plus 1 cross 1, beta is basically a scalar, it will be multiplied with each element of the vector. Okay. So, these two are the same formula that we derived yesterday, but now in matrix notation. Okay. So, these are the ones that you will actually use when you write a computer code. Okay. So, these are the ones that you will be using. Okay. So, these are posterior parameters computed using computed, that is all, not using. Okay. Posterior parameters computed, which includes the mean vector and the covariance matrix. Clear? This notation is clear, right? So, whenever I write capital phi, this is the thing that should, the design matrix should come to your mind, but whenever I write small phi, it's that row should become a vector. Okay. So, keep that in mind. Okay. So, now yesterday we did compute this, but what we did not compute was the predictive distribution, because the goal in any machine learning is that you want to learn a model, but your objective is not the model. Model is just the medium. So, the model is the medium to make predictions about new data. So, in machine learning you are always interested in making predictions, at least in supervised learning. Okay. So, in machine learning the objective is to predict y star or t star, let us say, corresponding to new input x star, right. This is your objective. Now, this is the objective in normal machine learning. In probabilistic machine learning, what should be your objective? It should still be something to do with t, but it now should be in a form of probability distribution. So in Bayesian machine learning, this reduces to computing the predictive distribution, and this is not the first time I am introducing the term predictive distribution. Can you remind me when we used it last time? In coin tossing, what is the chance or probability that the next toss will give a head? We use x tilde there, now I am using x star, but we did see this earlier, right. So, predictive distribution, so that is equal to probability of t star given x star comma x comma y, where this is basically your data, training data x comma y. Okay. X star is your new input and you are trying to find out the distribution of t star given x star and the data. Okay. Now, what do you do not see in this expression? What do you do not see in this expression? Parameters. You do not see a w, you do not see a beta, right. You do not see those in this expression. Okay. Actually, in this case, so this is the generic form. In this case, you will have beta, because beta you have assumed that is known to you. Okay. So, beta inverse or beta is known to you for this case at least. When you go later, you will also remove beta. So, right now you can actually write beta also, because the way we have solved it, it was more like beta is given or known, right. So, and not only beta, you can also write what else you can write, the hyperparameter. The parameter should not be there, but alpha should be there. So, it will be function of alpha. Okay. So, these are my hyperparameter. Beta is generally not a hyperparameter, but for this setup beta is known. Okay. But generally you will not see in textbook beta and alpha are written. Generally in textbook beta and alpha will not be written, okay, because they are like known, so you do not write them. You only write what is random and in that sense. Okay. So, generally beta and alpha are not written here, but it is actually a function of beta and.
So, hyperlinking completely.
Sorry.
AC से.
हाँ टेम्परेचर चेक करने के लिए टेम्परेचर चेक करने के लिए
टेम्परेचर चेक करने के लिए बोले.
Okay. So, beta and alpha are the.
Sir, why didn't you write W?
Huh?
Why didn't you write W?
You will realize that. Okay. You will let me come. So, W definitely we are not writing, because W is a random variable. So, that is a probability distribution. What will you do with that? But let me take that question. Why do not we write W? So, if I do not want to write W, what should we do? We should integrate it out by using the sum law. That is what is done, because the idea is you do not know W, you know the probability distribution of W. So, you have to marginalize out W by using the posterior distribution. So, this is equal to integration probability of t star given x star comma W comma beta. Now, your W is into picture, and can you tell me why is now x and y not there?
Because XY needs to predict W. So,
You are right. So, whatever information x and y were given,
it is in there.
it is in W, that is one point. or a more scientific answer is given W it is conditionally independent of the data. So that is the scientific statement, okay. That given you have once you have conditioned on W, your prediction T star will only depend on X star and beta. It will not depend on the training data, right. So that is a, yeah. And then, but on the left hand side W is not there. So that is equal to probability of W given X comma Y. So this is your data basically, and also your alpha, which is your prior parameter, and then you will integrate over W. Okay. So what law have I used here? See, first I have used the product law, then I have used the conditional independence to remove some of the terms, then I have used this sum law. Integration is a sum law. So this you are getting by using the sum and product law. Okay, that's all. Okay. So the first term is the basically the conditional, the second one is the posterior. Okay. The first term is the likelihood actually. The first term is the likelihood, the second term is the posterior distribution you integrate. So this is known as the predictive distribution. This is the exact thing that we did when we were trying to predict whether the next coin toss will yield a head or a tail. Actually we did head, and our answer was coming out to be alpha by alpha plus beta in the coin tossing example. In this case, what will be the answer? We don't know, we will have to see. Okay. So this expression is clear to everyone or not? This expression will error.
In the first term, why did we write beta comma alpha?
Is what T star, once you know X star and W and beta, what is the relation between them and T star? T is equal to W transpose phi x plus epsilon. So where is alpha there?
Does it not contribute to W?
Yes, that is, but once you fix W,
So how is beta there?
is beta contributing to W or it is because of epsilon there? Okay. So that is the conditional independence statement. You have to be very careful that once something is given that is known, now other things are kind of disconnected then. If you remove W, then it is a function of everything, and that is what you see on the left hand side. Any other question? So this you please study it. If you don't have a question now, please study it, and if you have question you can come to me, ask me later, because this you will see again and again. This is the main thing actually, one of the main things, so it should be very clear to you, okay? The predictive distribution. Okay, so now what is the first term? What is the distribution? I cannot work with P, I have to have some distribution. So what is probability of T star given X star comma W comma beta? What is the distribution? Normal, right? So this distribution, if I write it down, so that is equal to probability T star given X star comma W comma beta is equal to Gaussian. Why Gaussian? Because epsilon is Gaussian. Why is epsilon is Gaussian? Because of central limit theorem. All of those is coming back. I mean, okay, all of these things are there. So Gaussian of T star given, what is the mean? W transpose phi of X star, okay. But I will write it in the opposite form. I will write phi of X star transpose W. A transpose B is equal to B transpose A, right? It's dot product rule. So I will write it as phi X star transpose W, right? What is the variance of this? What is the other parameter? Beta inverse, right? Beta inverse. Again, this is the likelihood, it is coming from the likelihood. So it is the likelihood that is evaluated at the new input X star, okay. The second term is this one, and this one, what is the distribution? This one you should probability W given D, right? If I write it in compressed form, that is W given D. What is this equal to? This is the posterior of the weights. That is what we did for 70% of yesterday's lecture. And what was the final answer? It is a Gaussian with mean mu n and covariance S n in. So, this is equal to a Gaussian over W given mu n comma S n, right. This is the posterior distribution. The previous one was the likelihood evaluated at the new input where you want to predict. Okay. And now, I want to have solved this integral, right. So, I now have an integration over W where both my components inside the integration are Gaussian. Okay. So, what do you think the integration will yield? Gaussian, and that comes again from a theorem, not a theorem, a simple proof actually, that convolution of Gaussian over Gaussian gives you a Gaussian, because this is a convolution integral. If you remove the conditional part, you will realize it is nothing but the convolution integral, and convolution of a Gaussian with respect to another Gaussian yields a Gaussian. Okay. Now, I have not yet told you what are the parameters, we have to derive that. So, the statement is that convolution of a Gaussian with respect to another Gaussian yields a Gaussian. Okay. So, convolution of a Gaussian with respect to another Gaussian yields a Gaussian. Let me write it down in a generic term. Okay. So, suppose what should I take? Y given x, let us take. So, suppose, so example or of this is, and this is not an example actually, this is a generic case, probability of, suppose I have capital Y given x and I know that this is a Gaussian of y given a x plus b comma L inverse, okay, where A is a matrix, x is a vector, we are doing multivariate. So, A is the matrix, B is a vector, x is a vector, L is a matrix. Okay. And we also know that someone has told us that P of x is also a Gaussian over x parameterized by mu and lambda inverse. Okay. So, the first term is a conditional, second one is a x. So, probability of y is actually, so probability of y is equal to integration of probability of y given x, probability of x dx. So, this is basically the convolution of a Gaussian with respect to Gaussian. So, whenever you see a equation of this form, this is the convolution equation. Okay. And whenever it happens, so in this form you will get this to be Gaussian of y given the parameters I am not writing right now, we will derive it. Okay. Let us call it mu y and I do not know s y maybe. Okay. We will derive it. So, now my job is to find out mu y and s y. Okay. So, in the homework I will ask you to do this, solve this integration. So, that will be one question in the homework, but the parameters I am just finding out right now in using a different route which is very simple actually. So, let us look at the first expression. Okay. Y given x is a Gaussian with respect to, with mean a x plus b and covariance L inverse, right. Can I write it in this form? Y is equal to a x plus b plus epsilon, where epsilon comes from a Gaussian with 0 comma L inverse. Are these two expressions same? Y given x, y given x that you see and this expression, are they same? If you think they are not same, just think what will be the probability of y given x. A and B are fixed obviously. That will be a Gaussian, because of the same logic we had the likelihood to be Gaussian, right. So, now let us take mean of y. What is mean of y? If I take mean of this expression, what will I get? A mean of x plus b plus mean of epsilon will go to 0. So, it will be a expectation of x plus expectation of a constant is a constant plus expectation of epsilon will give you 0, because that is given here. Okay. So, this comes out to be a, what is expectation of x? Mu I guess plus b. Okay. What will be covariance of y? So, let us write S of y. So, I will take covariance of the right hand term. So, what is covariance of A x? A x A transpose. So, A covariance of x is equal to L inverse A transpose. Okay. What is covariance of a constant? 0. So, B will not contribute. What is covariance of epsilon or variance of epsilon actually, covariance when you take. So, that will come out to be sorry, not L, this should have been lambda, I wrote it wrong. This is covariance of x is lambda from last slide plus L inverse. So, I am taking variance actually if you realize, or covariance, but there can be a cross covariance that is 0. So, epsilon and x and epsilon are independent. So, that term is not there. Remember, covariance of A plus B is equal to variance of A plus variance of B plus 2 times covariance of A comma B. So, that is the thing we are using, but in a covariance form. Okay. So, you got this, that is your parameter. So, therefore, probability of y comes out to be a Gaussian of y given A mu plus b comma L inverse plus A lambda inverse A transpose. Okay. So, this was a little sidetrack. This has no relation as such with the linear regression that we are solving, but we are going to use it. Okay. So, let me put a line here which shows that this is we did because we want the green portion, not the green portion actually. So, to find the predictive distribution. Okay. So, now this is our expression, right. Now, I do not have it here, but you have it on your copy. So, tell me, by looking at this expression, what is my A? Y is equal to A x plus b, what is my A here? Phi x star transpose. Everyone agrees that A is phi x star transpose? So, I will write it down then. So, for our case, A is equal to phi x star transpose. What is B? It is not there, 0. Then what else we have? What is L inverse? What is L inverse? Beta inverse. Okay. What is mu? Mu is equal to our mu n, our posterior mean. What is our lambda inverse? Lambda inverse is our Sn. What is your random variable here? Is it when you are finding it out, what is your random variable? Is it W or it is X? Let me make it even simpler actually. Look at this expression. Whatever is constant A should not appear in the second probability. So, second probability was of X. So, that is why A was your matrix. So, now if you go back, what is there in the second term? W. So, that means W is equivalent to X. So, then A is equal to phi X star transpose. Okay. So, yeah, because of the notation X and X that happens, I understand that. Okay. So, anyways, these are my expressions, right. So, then therefore, predictive mean will be equal to, let us call it M. M is my predictive, N is my predictive mean because the model is trained with N training samples. So, predictive mean will be equal to, I will go back here and you tell me what is the predictive mean equal to. Phi X star transpose is your A, right. So, A will remain as it is, then multiplied by W, that is your X. So, X is supposed to be replaced by mu and your mu is mu n. So, then your predictive mean will be phi X star transpose mu n, okay, where mu n is your, what is your mu n? Posterior mean. This is the predictive, Mn is your predictive mean, mu n is your posterior mean. Okay. So, this terminology is, that is why I was introducing it or telling it again and again, because they will come back throughout this course. Okay. This was simple, the difficult one is coming. What is Sn? Not Sn I have already used, I will use sigma n now. Okay. So, sigma n is my predictive variance, covariance. So, predictive covariance. Okay. Let us call it, I mean, okay, I am writing covariance, but actually we will get a variance because I have assumed X star to be one point. You will only get covariance if I assume X star to be multiple inputs at a time. Okay. So, sigma n square, what will it be equal to? Here it is. What is your A? Phi X star transpose. So, that will remain. What is your lambda? Sn inverse. So, Sn, it will be Sn and A transpose will become phi of X star. So, let us write it down first. Phi of X star transpose Sn phi of X star plus L inverse. What is L inverse? Beta inverse. Now, beta inverse will be beta inverse or beta inverse I? It is a scalar, so there is no I. It will become I if I do it for X star is multiple inputs at a time. Okay. So, this I thing you have to be careful about again. Okay. So, this is your predictive variance, not covariance, I wrote it covariance, but then it is your predictive variance. Okay. So, when you are predicting, you are getting a not only a mean prediction, but also a variance which will tell you how confident is your prediction, how confident is your model about the prediction. Okay. Now, this prediction that you are getting has two terms, right. Predictive variance has two terms. What is the first term and what is the second term? Let us look at the second term. What is the second term representing? Noise in the data. If the noise, so your predictive variance would be a function of your noise in the data. If there is no noise, then beta will cease to exist. So that term will not be there, beta inverse will be equal to 0. So this term corresponds to the noise in the data. Okay. What is this term correspond to? What is this term correspond to? This term corresponds to, there is a capital N I see there, capital N. So this corresponds to that you have trained from n number of training data. If n goes to infinite, this term will become 0. So that means ideally that your source of uncertainty is, there are two sources of uncertainty. One, you have limited data. If your data is infinite, that source of uncertainty should vanish. Second, your data is noisy. If data is not noisy, that source should vanish. And if you are working with infinite data and clean data, then you should not have any uncertainty. Then both the terms will go to 0. Okay. So this is because of limited data. And this is the beauty of Bayesian, that here you can prove mathematically that if you have infinite data, this term will be 0. If you have no noise, the term will be 0, and if both happens, this is supposed to be 0. Other probabilistic methods are also there, which we will somewhat discuss. Let us say for example ensemble, that is also give up, but that will not have this property. Okay. So definitely you cannot prove that. Okay. Clear? Any doubt on this part? I said 20 minutes, right? I took 45 minutes. Okay. Yesterday I said no, I will take another half an hour, 20 minutes. Okay. So I have another 45, no, not 45 minutes, half an hour kind of time. So let us, we will start with the second part. So what was the issue with all the derivations we did since yesterday?
Sir, how will it go to 0? When entering state will go 0.
How will that term go to 0? Sn will go to 0, and that is a homework, so I will not prove it. But you look at the expression of Sn, you will see that there is a summation I equal to 1 to n, phi xi transpose like that, right? So that is a square. So if you keep on increasing, adding infinite number of squares, so infinite number of positive numbers, that is go to, so from there it will come, because Sn inverse will go to infinite, so Sn will go to 0, obviously, okay, because the term you are getting is, remember, beta summation I equal to 1 to n phi xi transpose. So that is the square term, and you have infinite number of those summations, that will give a infinite kind of very large number, and Sn is 1 by that, but I will give that proof. Now, although I told it, I will give that, okay, because it is for your practice, and you will only remember this thing when you do it by hand, and that is why typed homework is not accepted, because even if you are copying, you copy it and write it. Okay. So discussion is allowed, by the way, but if you submit the same thing, then you might get negative marks. Okay. Okay, but I am okay with you discussing, forming a group and discussing, that is fine, for the homework I am saying. Okay. By the way, that reminds me that yesterday I have already circulated the project topics. Last time I saw that I think 6 groups also have provided their options, others also provide, otherwise I think it is ending when? Day after tomorrow, I think 15th night. After that I will just start randomly assigning. Okay. So yeah, and some of those topics I have given, I have already associated papers with them. So your job is reduced if you select those. For others, you have to then come up with a paper of your own in the area. Okay. And I have asked for 5 options, but seems like I should have asked for more, because already I saw that one student has provided 5 options and he will get none, the 6th student, because all the 5 options is taken by the first 5. Okay. But that is okay. In that case, I will get back to them. Okay. So now we have done this derivations and all those things, but what was the assumption in our derivation? Beta is known, which is not the case in general. So let us now go to the case where beta is unknown, or rather we will now consider sigma square to be unknown. Okay. You can do it with beta also, we will do it sigma square, because so that I can show you both the way of doing things. So till now we assumed beta inverse to be known, right. However, that is almost never the case apart from certain cases, one example I gave yesterday. So, that is never the case.
Sir, please go to previous slide. So, sir, our aim was to find the prediction that for x star, what we will get t star. So, sir, suppose if we are working with infinite and clean data, that means that our prediction should always be that mn.
Mn. Your prediction is anyways Mn. Your prediction mean will be the, so it will become a point estimate then. So, suppose what is the point estimate? It is a distribution where the variance is 0. So, in this case what you are getting is, you are getting a distribution, the variance is 0, the mean is still there. So, it is a delta function, direct delta function at Mn. So, that is the distribution you are getting.
But sir, like suppose if the data follows some pattern, the data is very clean, there is no noise, but there is some pattern.
You are mistaking. Mn is a function of x star. So, if x changes, the mean will change. It is not a constant value. So, if the x changes, the mean will change. It is not a constant. It is a function of x. Okay. So, what you are saying is there is a pattern. The pattern can be sinusoidal. Let it be. So, that phi x star is there, na? So, it is a function of x star. I understand when I say there is, it is a constant, your mind goes to univariate case where it is a value. It is not a value. It is a function of s. So, actually this is actually not a random variable. It is a random process if you think about it. We will talk about it when you go to Markov process, but it is actually a random process because your Mn is changing with x and is random. Okay. So, it is known as random process. Okay. So, now for a realistic setting, we now consider beta inverse, which is equal to sigma square, okay, to be unknown. Okay. So, now we are assuming sigma square to be unknown. Do you think, or what do you think will change in our derivation? First, remember, first we have to find out the posterior, and then using the posterior we have to find out the predictive distribution. Okay. So, let us start with the posterior. Now, how do you compute the posterior? By using the Bayes law, basically by using the likelihood and prior. Now, there is likelihood and there is prior. Now, for this case, what change you are expecting in the likelihood, if any? Okay. Go back and check and try to think that whether anything will change in the likelihood. What was the likelihood we are getting? Remember? Okay. Remember? So, previously our likelihood, or to be more specific I should mention data likelihood, but I am writing likelihood. Likelihood was of the form probability of t given x, right, comma the parameters theta. So, given w and beta inverse, I am writing sigma square now, was equal to a Gaussian of t given w transpose phi x. This is for a single data, remember that. Actually, I should write, okay. So, how I wrote it, I should write the same thing. I wrote it as a product, if you remember, I equal to 1 to n, because the data were IID, remember, and then probability of Ti given xi comma w comma sigma square that is what I wrote, which is equal to product I equal to 1 to n, each of these were Gaussian, T I given W transpose phi x I comma sigma square, right. This is what we took or wrote last time, and this is coming naturally because our noise is assumed to be Gaussian. Now, for the case we are taking now, do you expect any change, or do you think it should be same? So, will the Gaussian change? Whether the
We aren't making any assumption over here.
what assumption are we making?
We aren't making any assumptions. It shouldn't.
Correct. So, it should not change exactly, because our likelihood is theta given theta. So, whether theta you want to infer or you do not want to infer, that is always in the conditional side. So, even if I want to infer sigma square later, that does not change my likelihood. Sigma square will still be in the likelihood on the right hand side only, conditional variable only. So, it should not change. It should, because that expression has not changed, t given x comma w comma sigma square, that is as it is. So, if that is as it is, everything else is as it is, why should it change? Right. So, this should not change, and this expression I am now, so basically here everything remains the same. Okay. So, theoretically nothing changes, but practically does anything change? So, if you think about it practically what were we doing? We were only taking the exponential term, because that was the only term having w. But now I have to take also the terms that is having sigma square. So, outside also there is a sigma, that should now come into picture, right. So, practically things will change, because now I have to operate on the outside term also, but theoretically it does not change, it remains the same. Is this clear what is happening? Because the distribution we are trying to find, the likelihood is probability of data given theta, and we are still finding out probability of data given theta. Theta was having w and beta inverse, theta is having w and sigma square. Data was having t given x, data is having t given x. So, since that term is remaining same, it should remain same. Clear? So, nothing should change in the likelihood from a theoretical point of view. It should still be a Gaussian. Okay. So, probability of t given x comma w comma sigma square will be a Gaussian. So, now I am writing in a, I am using the product and writing in a multivariate Gaussian form by using that product sign. I am not writing the product. So, now it is in a multivariate form, same thing, t phi w comma sigma square I. So, w transpose phi became phi w because phi is transpose. Remember the design matrix I saw earlier? This was what I was building it for. I was going to use this thing, so that is why this was used. Okay. And sigma square was sigma square, I have to use a I now because it is a matrix. So, instead of the product now I am writing it in a multivariate form. Now, which is proportional to? So, can you tell me what should I write now? What is the multivariate Gaussian look like? 1 by 2 sigma square to the power n by 2, 1 by, so sigma square to the power minus n by 2. That comes from the determinant of sigma I. So, if you take determinant of a diagonal, it is a product. So, this is proportional to sigma square to the power minus n by 2 Okay. The pi term I don't care about, that is a constant. So, pi I am removing. Inside the exponential, what will I have? So, previously I wrote minus beta by 2, I have to write 1 by 2 sigma square, 2 sigma square, and then I have t minus phi w, I will write phi w minus t, and you know why. So, I will write phi w minus t transpose, then the I should be there, I inverse does not matter, they are same. So, I am not writing that. Then phi w minus t. Okay. Clear? I have given all the brackets, yes. So, the likelihood remains the same. The only practical change is that I have now included that sigma square to the power minus n by 2, because sigma square I now will have to infer. I have my posterior will now be probability of w comma sigma square given theta. So, my posterior will change, and so that sigma square will have a role to play. Okay. So, what is the next thing? This was the likelihood, right? Let us call it equation 1. I guess today I have not numbered any equation, so let us start with 1. What is the other term? Prior. What do you think, will anything change in the prior? It should not, is the answer. Anyone thinks it should change? So, now what are you trying to infer? W and sigma square. So, do not you need a prior on sigma square? How will you infer sigma square without a prior on sigma square? So, you are right that for W it should not change, but you will need a prior for sigma square, or rather you will need a prior for the joint distribution, because sigma square is unknown. So, I need to infer sigma square. So, I need a whatever is unknown is now random, uncertain, and whatever is uncertain we will assign a prior to that. Remember the philosophy, whatever is unknown is uncertain, and whatever is uncertain is to be inferred, and whatever is to be inferred will have to be inferred using a prior and likelihood. Okay. So, since sigma square is also unknown, we have to assign prior over W and sigma square. Okay. So, how many total parameters you have now? How many total parameters do you have now? K plus 2, W is K plus 1 plus sigma square is 1 parameter. So, K plus 2 parameters. So, it is not 2 parameter, it is K plus 2 parameters. So, although I am writing in this form, remember always that W is a vector, K plus 1 dimensional vector, and so it is a distribution over K plus 2 parameters. Okay. So, my prior will now be, and I will use what kind of prior? What type of prior? Conjugate. And the conjugate prior for this case is Gauss inverse gamma. Gauss inverse gamma. So, Gauss over weights, we already saw that, inverse gamma over sigma square. So, our prior is probability of W comma sigma square, which is equal to Gauss inverse gamma over W comma sigma square given Wn. Previously I took Wn to be 0. In our previous derivation I took Wn to be 0, and now I am making it general. So, I am taking some Wn. Then Vn, which is a matrix, comma, sorry, not Wn, W 0, the Vn will be my posterior, comma A 0, comma B 0. okay, which actually is nothing, it is a product of Gauss and inverse gamma, that is all it is, okay, but it is written in this form, which is then equal to Gaussian over W given W naught comma sigma square V naught and then inverse gamma over sigma square given A naught comma B naught. So, this is the Gauss inverse gamma. Okay. So, it is basically probability of W given sigma square multiplied by probability of sigma.
Can you explain the prior again?
Can I explain what?
The prior again, what did you write this?
Yes. So, okay. Let us start from here. So, the prior will be this one, that you understand, right? This is my prior, this you understand, right? Now, this is I will write in product rule. What will I get? Probability of W given sigma square, probability of sigma square, right? Now, previously the derivation we did, we were working with only W given sigma square because sigma square was known, and for that case the prior was Gaussian. I took it to be Gaussian. Sigma square is the new thing that is coming, and you can use any prior, but I want to use conjugate prior because I want to derive it, and for sigma square the conjugate prior is inverse gamma distribution. So, that I have written. Okay. So, I did not write this expression, I directly went there. Okay. Clear? What has been done? Yeah. Okay. So, that is what we have done, which is we have now introduced the Gaussian, which is the conditional, and the inverse gamma. Okay. Now, one question. Previously, we did the derivation with beta inverse, right? Now, I am doing it with sigma square. Okay. So, suppose I want to do the derivation with beta inverse, I can. So, in that case, it will be probability of W given beta multiplied with probability of beta, right? In that case, can you guess what will be the prior? Will it be same if I do it with beta, or something will change? And it is in the name itself. If you think about the name, you will get it. For sigma, you understand the question? Now, we are doing the derivation with sigma square. The last derivation we did was with beta inverse. Beta inverse is equal to sigma square. So, now suppose I want to do this derivation with beta. Do you think my prior will change? Yes. Exactly. So, I said it is in the name. So, beta is inverse of sigma square. So, what is inverse gamma should become gamma. So, that is why I said it is in the name only. So, if you do it over beta, then instead of inverse gamma distribution, you have to use gamma distribution, because beta is inverse of sigma square. What is beta? 1 by sigma square. Gamma is 1 by gamma, 1 by inverse gamma. I mean, that is the inverse distribution, right? So, if x equal to 1 by y, if x is gamma distributed, 1 by y is inverse gamma distribution. Okay. So, it was simple, but you should keep that in mind, okay? Because in books you might find this distribution with gamma. It is the same distribution, just that they have used beta instead of sigma square. Actually, in the book, it is with gamma. Okay. I am just doing it with inverse gamma. Okay. Anyways, so now one thing I have not covered, and that I will cover now, what is the PDF of gamma distribution, because we will need that, or inverse gamma distribution. So, first let us write this. So, this was for explanation, right? So, I will make it a box. So, first I have to write the Gaussian part. For how will the Gaussian part look like? Is proportional to. So, what should I retain, what should I not retain from that Gaussian? You know Gaussian enough by now, should be able to tell. What do you think will be written? What will be the first term? Should I start with exponential or should I have something outside? That is the first question. And what should be outside? Sigma square to the power minus, then it was k by 2, because W is k actually k plus 1 by 2, okay, but I will call it k prime, okay. I do not want to write plus 1 every time. So, I will call it k prime. So, this is equal to sigma square to the power minus k prime by 2, and remember k prime is equal to k plus 1. Actually, I can write it with k by 2, by the way, because generally, and I will cover it later, but I am just giving you a spoiler, that generally you do not do Bayesian over the bias term, you only do Bayesian over the other things, and then bias is found out from back calculation. So, generally you do Bayesian over W1 to Wk, and then using those you find out W naught. Okay. And we will have a separate section on that later, not today, but for now I am just writing it for derivation sake using k prime. Okay. Then what will be after that in the Gaussian term? Exponential of minus 1 by 2 sigma square, and then inside W minus W naught transpose V naught inverse W minus W naught, right. Clear what I have done? Basically the simple Gaussian expression. Now come to the inverse gamma. Now, inverse gamma, as I say with any other distribution, you do not need to remember the total distribution, but you need to remember the variable components. I mean, you should be able to identify, right. Now, inverse gamma takes the following form, it is over sigma square. So, it will be sigma square to the power minus a naught plus 1 exponential of minus b naught by sigma square. So, this is how the inverse gamma distribution looks like. Okay. Sigma square to the power minus a naught minus 1. So, minus a naught plus 1 in bracket exponential of minus b naught by sigma square. Okay. This is the unnormalized form of the inverse gamma. If you normalize it, you will get a gamma function and all those things will come. That is why the gamma, it is called gamma distribution, gamma function will come from there, but this is the unnormalized form. Okay. So, let us write it down. So, this is unnormalized distribution of inverse gamma. Okay. This is the unnormalized distribution of the inverse gamma. Okay. So, we got the prior also, let us call it what, equation number 2 maybe. Right, previously you wrote the likelihood. So, I have my prior, which is equation number 2, I have my likelihood, which is equation number 1. What will I do next? Posterior. So, let us find out the posterior. So, therefore, using equations 1 and 2, we get probability of W comma sigma square given the data, which is t and x. So, I will write data. This is proportional to probability of W comma sigma square prior times likelihood t given x comma W comma sigma square. Okay. Now, a big calculation is coming, you can understand, because the prior itself is of 2 line, likelihood is of 1 line. So, we have to do all those calculations. So, let us do, which is then proportional to w comma sigma square, I will write this 2 line expression. So, actually I can combine, if you look into it carefully, I can combine the 2 sigma square and I can combine the 2 exponential. Sigma square I will not combine, although I can combine, I will not combine. Exponential is the only thing I will combine. Clear? So, sigma square will be minus k dash by 2 and then sigma square to the power minus a naught plus 1. Okay. This is only prior I am talking about, remember. And then exponential, inside that I am now going to combine the, I am not the prior, I mean prior and likelihood both, but yeah, okay. So, minus 1 by 2 sigma square and then I will have w minus w naught transpose v naught inverse w minus w naught plus 2 b naught. Clear what is happening? Why 2? Because it was by sigma square. So, I made by 2 sigma square, that is outside, so 2 b naught. So, that is why 2. Clear? Other things I think is simple. So, this is my, so let me just mark it in color. So, this is coming from Gaussian, this portion is coming from Gaussian, this is coming from inverse gamma, this b naught is coming from inverse gamma. Okay. So, just to put thing into perspective what I have done. And now, I will do something what is known as completing the square. So, that means I will open up the terms inside. I think I missed one term, right? Yeah, there is one term in prior I have missed, the Gaussian prior I have missed. No, the likelihood. The likelihood has been missed. Okay. So, that has to be also be included. So, anyways, so it is good that I missed, because that means I have only written the prior till now. So, now the likelihood is coming. So, let us write the likelihood. The likelihood is sigma square to the power minus n by 2 exponential of minus 1 by 2 sigma square, and then what do I have? Phi w minus t transpose, I think that is all, yeah, v is not there, sorry. Phi w minus t. Okay. I have 6 minutes. So, let us just combine the 2 terms. I will not be able to complete it, okay. But let us combine the 2 terms and see. So, now what will I do? I will do a product. So, let us see how will I do the product. Exponential and exponential I will do, you know what will do, I will just add them up, right, inside the exponential. But this sigma square, this I will only do with, I will include with this term. So, the 2 blacks I will combine, the cyan I will keep as it is, and the exponential I will put everything together inside. So, this is then equal to sigma square to the power minus k dash by 2 sigma square to the power minus a naught plus n by 2 plus 1, right. And from here you should be able to see what will be my updated A, what will be my posterior A naught plus n by 2. So, that is going to be my posterior A, which we will do next time, but you can directly see it from here. And then let me write it here, exponential its total product that is going on, okay, minus 1 by 2 sigma square, and then you have W minus W naught transpose V naught inverse W minus W naught plus B naught I will write at the end. So, B naught I am 2 B naught I am not writing, the likelihood term I am writing now, phi W minus T transpose phi W minus T plus 2 B naught. Okay. And now, let us open the bracket inside the exponential, that is all I care about now. So, all those things I will write in quadratic form like we do in Gaussian, W transpose W and all those things. So, this is then equal to sigma square to the power minus k dash by 2 sigma square to the power minus a n plus 1, where this I am now writing as a n. Okay. And then exponential minus 1 by 2 sigma square remains outside, and let us see what do I get. So, first term I will get is W transpose V naught inverse W, right, W transpose V naught inverse W, right, clear. Along with that, what will I get? The second term minus 2 W transpose V naught inverse W naught, right. The third term will be W naught inverse, so W naught transpose V inverse W naught, right. So, I am writing it here plus W naught transpose V naught inverse W naught. So, this is the first bracket I have opened. Come to the second bracket plus the first term will be W transpose phi transpose phi W, W transpose phi transpose phi, continuously check the dimension when I am writing these things, like phi is n cross k. So, phi transpose will be k cross n multiplied by n cross k will be give k cross k, and then W is k cross 1. So, W transpose is 1 cross k. So, you will get a 1 cross 1. Okay. The second term is minus 2 W transpose phi transpose T, because phi is n cross k, phi transpose is k cross n, T is n cross 1, you will get a k cross 1, and then W transpose is 1 cross k. So, you will get a 1 cross 1. So, each of these should be a scalar, because inside PDF everything should be a scalar. Okay, what is the last term? T transpose T, right? T plus 2 B naught. Okay. I think I will stop here, but the next thing we will have to do is we have to combine this term to come up with an updated Gaussian and an updated gamma. So, what will you need? You will need, look at it, there is V naught, you will need a Vn, there is W naught, you will need a Wn, there is B naught, you will need a Bn. These are the three things you have to arrange this thing in such a way so that you can come up with a Wn, which is an update of W naught, Vn, which is update of V naught, and Bn, which is the update of B naught. An we have already computed. So, I will stop here for today. Next class we will first finish this and then do the predictive of this, which will you can understand what will it will look like. Okay. So, and that will wrap up our Bayesian linear regression. Once we are done with this, and once we wrap up Bayesian linear regression, we will actually start sampling, okay, because conjugate prior is very limiting. So we don't want to be constrained or limited. So we will do sampling and all those things once this is done. And all of those we will be doing on this problem only. So this linear regression that we have started, Bayesian linear regression, we will do Bayesian linear regression with conjugate prior, then we will do Bayesian linear regression with sampling, different sampling, then we will do Bayesian linear regression with variational Bayes expectation propagation, and only after that we will go to Gaussian process and other stuff. Okay. So we will be staying at this same problem for some time. Okay. So we will stop here. Thank you, and I think there is a break. When is the next class apart from tomorrow? Thursday is holiday. So okay. So there is a long gap. So probably some of these I have to repeat, or you have to check before coming to the class. Okay. Thank you.